Okay, so this is the second lecture, and I'd like to start by asking if there are any questions about what I did last time. Are there any? Okay. There is one small correction from what I did last time, which I won't even bother, except that since this is on video, it's really embarrassing. If some technical detail is not cleared up. And last time, it's a very minor error, it won't affect anything that we do. But last time, I had said that because this Lorentz group is like a product of two SU2s which are complex conjugates of each other, this would transform in this way. And the thing I said wrong was that this matrix is unitary. Of course, this matrix should not be unitary because it's in fact not a compact group. This is an SL2C matrix. But actually, it's very much like a unitary matrix with some i's in the wrong place. And this has to do with exactly that fact that the two SU2s in this problem are J plus IK and J minus IK. The fact that you have two SU2s with these generators is the same as saying that you have SL2C. That's the actual group. And so these are matrices of SL2C. And but the fact that I used last time, that for example when I complex conjugate this turns into a dotted index, or the fact that if I contract a raised and lowered index then it's an invariant, these all remain true. In fact, contracting a raised and lowered index makes an invariant because of the determinant of this matrix being 1, which is true even in SL2C. That's just a very minor, so U is not unitary. The problem really is that, you see, SL2C is a non-compact group with 6 generators. We are not used to dealing with groups with 6 generators. It's too much for us to comprehend. While SU2 is a much simpler group with 3 generators, and we have sort of figured out all the algebra of SU2 and its representations. And SL2C conveniently splits into this, but because of the i's, this is not really a product. SL2C is not actually a product of SU2 cross SU2, but for almost all purposes it behaves like one as long as you are careful about these i's. Okay. Well, as I said, it won't change anything we did last time. Okay. And the other thing which I hope you all know, since I hope you are all signed on to the mailing list for this course, there is now a web page for the course, and the videos of the lectures are up on that web page after each lecture as soon as we can get it done. So if there's anything that needs to be reviewed by you or any of you misses the lecture, you've got it there. You can do it. Good. So where did we reach last time? We reached basically the following, that we had massive gauge bosons after the Higgs mechanism. And they had masses mw plus and minus, which are V by root 2 times the coupling constant G2 of SU2. Yes?
Sorry, I think this.
Right. Good. So the mass of the W was the coupling constant of SU2 times V by root 2, and V is the Higgs left. And the mass of the Z was likewise some factor square root gy square plus g2 square v by root 2, and this is actually the same as the mass of the W divided by cos of theta W. We defined the Weinberg angle last time, and it's cos, right? So these were the two things we concluded from last time, and this takes care of 3 of the 4 gauge bosons from SU2 cross U1, namely the W plus, W minus, or W1, W2, it's the same thing. And this is not W3 and it's not B, but it's a linear combination of W3 and B. Okay. And another linear combination of W and 3 is massless. So let's just review that. So Z mu is actually cos. So Z mu and K mu as a 2-component vector is cos theta W, sin theta W. Here there's a minus. Sin theta W, cos theta W on W mu 3 and B mu is the hypercharge field. Good. Okay. Now this is the point where we ended last time. And we have to ask ourselves the question, okay, in this theory, what is the physical electric charge? So what we've shown is that this linear combination has a mass given by this formula, and this linear combination has no mass, okay, and that uniquely makes it the photon. Therefore, whatever couples to this thing will be the charge. And to see that, we can recall that the covariant derivative on the Higgs field was d mu plus I g2 w mu 3 times sigma 3 by 2 plus I gy b mu. So this whole thing is a 2 by 2 matrix. Here it is identity and here is sigma 3, and it's acting on the two component phi. Okay. And if we rewrite this by solving for w and v by inverting this matrix back in terms of z and a, then we find that there is a term which is I. It's a very easy exercise. Sorry, 1 0 0 0 a mu on phi. Okay, and the dot is the term depending on z. Okay, we expect this to take this form, and in fact I'll write the more general form when phi is replaced by any other field. Here phi is the Higgs field, and so it's natural to identify the electric charge E as the combination which couples to a mu. Again, this is an abelian charge, so you can really never identify it. You just have to measure things in units of that. So what we've basically done is to declare that this is E, and therefore phi equals phi upper and phi lower. Phi 1 and phi 2 was my previous notation. As per this matrix can now be written phi plus and phi 0. That means the Higgs field, the two component Higgs field, has an upper component with plus 1 charge and a lower component with 0 charge. Okay, that comes from this matrix, the structure of this matrix. So its charge is plus 1 and 0 in terms of E. Now, logically, this is not what I should have done. I should have first asked what the charge is of the electron, because that's the first object whose charge was identified. So if everything has come out right, then eventually the electron better end up having charge minus 1, but it will have. So this is okay. So let's show that the electron, let's see how the electron comes out to have charge minus 1. For that, I just have to rewrite the same equation, but on any field, in particular any fermion, since they are the only fields in the theory besides the Higgs that carry any charge are fermions. But we've already identified the charges of the W's, so that only leaves the fermions, and in that case, the same matrix comes out to be d mu plus I E. So now E is this thing, times 1 plus y, 1 minus y. Minus 1 plus y, and this is 2 here. This is on any other field that you have. That comes just by putting a y by 2 factor over here. Okay, I think I might have made a factor of 2 error here. Yeah. Here there was a 2, because y of the Higgs field is 1 in our conventions. Okay, but if I had left an arbitrary y over there, it would have appeared in this form. And you can check that when I put y equals 1, then this becomes 0, and this 2 gets cancelled by this 2, and I get the form that I got for the Higgs field. So this is the generalization of that. Okay. So what does that mean? It means that the up component of an SU2 doublet has E equals a half plus y by 2. Take this to there, and the upper component, and the lower component as E equals minus a half plus y by 2. Okay, but of course the upper and lower components of a doublet of SU2 have I3, the 3 projection of the SU, the 3 component of the SU2 charge being half and minus half. So I can identify this first number with I3. Okay, I3 is a half for the up work for the neutrino and it's minus a half for the down quark or the electron. Therefore, we get the relation that electric charge Q is I3 plus Y by 2. Okay, is that clear? I see everybody looking very blank today. Either this is something you know very well, in which case I am happy to go on, or something else is wrong. Please interact and tell me what is the case. I am not going to go until somebody answers this question. What? There's something I should repeat.
I think it was very.
Then why is everyone looking blank? No, you're most welcome. It's not like that. It's just that if it's puzzling, I'm prepared to explain it. I'm reviewing something that people are supposed to know, but if there's any puzzle, I'm prepared to explain the puzzle. You have to tell me that this thing is puzzling. I think people are finding something puzzling and they're not. That's my reading of it, and they're not telling me. Okay. Good. Now with this formula, we can finally complete the thing that we left uncompleted last time, which was the hypercharge assignments of all the fields. So if you remember last time, we had left the hypercharge assignments undecided. But now we can come back to all the fermions in this problem and work out what Y should be, because we know what I3 is, and also since they are physical particles, we know what their physical electric charge is. So we just invert this equation and find out their Y. Okay. So the first thing to do is the up and down quark left doublet. Okay. So here the electric charges are 2/3 for up and minus a third for down, and I3 is a half for up and minus a half for down. Okay, so between these two, I find that Y of the left-handed doublet is 1/3. Okay, notice a common Y, despite the fact that the electric charges are different and the I3s are different. This is not as much of a miracle as it may seem. The whole point is that the electric charge of the up and down quark differ by 1 going down. That's exactly what encourages you to put them in a doublet in the first place. Same is true for neutrino and electron. They differ by 1 going down, and that puts them in a doublet. So that guarantees that the hypercharge is going to be the same for both members of the doublet, which it has to be. Okay. Here I also mentioned that Treskin and many other people use a different convention in which the hypercharge is a half of what I am calling it. For them, this will be 1/6. Okay, that has some advantages which I'll point out, but I am following Breslow, Dole and Royce, so this is their convention. Okay, the neutrino and electron left-handed doublet. The electric charges are 0 and -1. That was you.
Sorry.
The electric charges are 0 and -1, and the I3 is half and minus half, and from this it should follow that YL is equal to -1. Okay, so Y, I think my notation was this is Y of QL and this is Y of LL. The quark and left-handed doublets. Okay. For the antiparticles, which will be right-handed antiquarks and right-handed antineutrino and anti-electron, the Y assignments will just be opposite. Next we do this for the singlets. So for the singlets we have U, R, P, R, neutrino, R and electron R. As I mentioned last time, the right-handed neutrino doesn't appear in many textbooks because there was not thought to be a right-handed neutrino, but now that we know neutrinos are massive, there are right-handed neutrinos. However, because of subtleties associated with neutrino masses, in particular the possibility of Marana mass, it's good to discuss neutrino masses sort of separate from everything else. And so at this level of review of the standard model, I'll be essentially ignoring this object. Still, for completeness, nothing stops us writing down its hypercharge. And the hypercharge for all of these, because these are SU2 singlets, the I3 is 0. So the hypercharge Q is just, the electric charge Q is just the hypercharge by 2. Okay. And so obviously we can choose a hypercharge independently for each of these 4 to make the electric charge what it is. So therefore the hypercharge here is 4/3, here is minus 2/3, here is 0, and here is minus 1, minus 2. Okay, so that's very easy. Now you can also see what's the merit of the Peskin et al. Conventions. In their conventions, Q is equal to Y for right-handed objects. So for the right-handed objects, the hypercharge is the same as the electric charge. That's somehow nice. Okay, here the hypercharge is double of the electric charge, but it's very minor. Good. Okay, so that completes the hypercharge assignments for all members of the first generation. And it's since generations are essentially copies at the massless level, we haven't put any mass terms yet, and we'll be discussing that soon. Apart from masses, the generations are just identical copies. So every generation of quarks and leptons will have the same hypercharge assignments as the first generation. So we've actually done it. There are no more hypercharges to be assigned. Okay. Good. So now we turn to a discussion of masses. In a way, we already discussed masses because we identified the masses of W plus minus and Z last time. So the things that remain are the Higgs and all the fermions. Okay. So let's look at the Higgs first. So here the first question is, how many Higgs particles are there in this model? We started with the doublet Higgs, upper and lower components both complex. That corresponds to how many particles? 4 real particles, or 2 complex particles and the antiparticles. And complex is more natural in this case because phi, the upper component, is charged. So it would have been a phi plus and its antiparticle phi bar minus, and then 2 phi zeros. But that isn't really the spectrum at all because of the Higgs mechanism. Okay? And in the process of the Higgs mechanism, very simple counting can tell you that we had 3 vector bosons, gauge bosons, that became massive. And massive gauge bosons have 3 polarizations while massless have 2. So one of those polarizations has to come from a Higgs. Okay, that means that in making 3 bosons, 3 gauge bosons massive, we have lost 3 out of 4 Higgs fields. When we say we have lost, we mean that these do not correspond to any physical particles of the theory. Okay. Now then it's up to us to identify which is the one that is in class. That means there is one real one left. Okay. Which is again a very nice thing because even at this very naive level, just doing some manipulating some Lagrangian, we have a phenomenological prediction that the Higgs of the standard model has to be neutral because it's one real field, can't be charged. Okay. So we are left with one real Higgs particle, and right now we want to find its mass in terms of standard model parameters. Okay. So the question is, how do we identify it? From phi plus phi 0. Now again, there are formal ways of identifying it, but the most simple way is to think what the Higgs mechanism is doing, or actually to think what spontaneous symmetry breaking means even before you do the Higgs mechanism. And what it means is that you have a potential for some fields which have some flat directions and some non-flat directions. Okay? When the wave settles into that minimum, then at the minimum there is a flat direction, or there are many flat directions. Each of those gives a Goldstone boson. And then if there are gauge fields in the theory, then the Goldstone boson is actually not there. Instead, there's a massive gauge field. Okay. The direction which is radial in the potential, that is, if this is the well and these are flat directions and that's the outward direction, it's that direction in which there's going to be a massive field. So we just have to identify the radial direction from this doublet structure, and that's particularly easy in this case because the wave of the Higgs was 1 by root 2 0 V, and V was a real number and it's the only number that's fixed by minimizing the potential. Okay, that means that if the original field phi plus phi 0 takes the value 1 by root 2 0 V, then it's at the minimum. Okay, now what's going to correspond to the oscillatory mode is the one where instead of V we have some other value in this component. Real part of this component has a different value than V. Okay, that's clearly out of the minimum. Okay, so that's the radial component. So the radial component, radial is a generalized term here because it's a 4-dimensional potential. It's a little hard to imagine, but the radial component eta is defined by phi plus of x, phi 0 of x is 1 by root 2, 0 and v plus eta of x. Okay, which means that the imaginary part of phi 0 and the real and imaginary parts of phi plus are the other three, the gauge directions. Okay, and of course there should be 3 because there were 3 gauge symmetries that were fixed. So all we need to do is choose phi plus phi 0 like this and find out the couplings of eta. How do we find out that? The potential of the Higgs was minus mu squared phi dagger phi. This phi, I hope you remember, is the notation for the 2-component object, and plus lambda phi dagger phi squared. So into this I plug in this form, I expand out, and at the end I get mu squared eta squared plus mu root lambda eta cubed plus lambda by 4 the fourth. So we see many things. We see first of all that this does not have eta to minus eta symmetry at all. Okay. Secondly, we see that there is a perfectly positive sensible mass term, and the mass of the Higgs is square root of 2 times mu. Now this may make you wonder because after all in choosing this parameterization I have already assumed a normalization for eta. Okay, and the answer seems to depend on that. The reason it doesn't, of course, is that the kinetic term first should be correctly normalized as half del mu eta, only then I can read out the mass. So I am claiming without proof that with this root 2, of course you know this because these are complex things, when I decompose with 1 by root 2 into real and imaginary parts, then I get conventionally normalized kinetic term. And with that, this is the correct statement. Okay. So here's another phenomenological result for the string theorists to appreciate, which is that the Higgs mass is determined only by mu, while the W and Z masses are determined by V, which in turn is determined by a ratio of mu squared and lambda. Okay? The W and Z mass are both proportional to V. The Higgs mass is not proportional to V, but only proportional to mu. We'll come back to this fact. Okay. Good. So that settles the issue of the Higgs mass. And now we finally come to fermion masses. Now right away we see that there is no SU2 invariant combination you can make from the spectrum of the standard model, which is a mass term for fermions. Okay. To remind you, we are working in this 2-component spinor notation, in which a mass term has to contract an undotted with undotted or dotted with dotted. Okay, and of course it has to be SU2 invariant, but the left-handed guys are doublets and the right-handed guys are singlets. And basically it's impossible to combine these in any sensible form to make a mass term, except if the field has no electric charge, and that is true for the neutrino only. In that case you can have a Majorana mass. in no other case, you can write a mass term. So no possible gauge invariant mass terms except for neutrinos. Okay. If these statements are not obvious, of course, I would very much urge you to check it and try it yourself to see if you can write one. Okay. Good. Now, what's going to help us is that the Higgs field is present and it's a doublet of SU2. And so I have a chance to write with the Higgs field. I can hope to write something which involves a fermion in a doublet. Let's say, let's keep the SU2 index. This is SU2 weak, not the SU2 cross SU2 of the Lorentz group. Okay, so this I can take a left-handed guy. I can contract it with the Higgs field. So this is a SU2 weak singlet, and then I can contract it with some other fermion which is right-handed. Okay, and if I put a dagger here, then this will be, if the left-handed were undotted, with the dagger it will be dotted. This is dotted, so I can contract this two. This is a schematic picture. I'll write the more precise thing later. I just wanted to see what is being done here. With the SU2 doublet left-handed fermions and singlet right-handed fermions, the thing that I can do is to contract the dagger of a left-handed fermion with the right-handed fermion. That takes care of Lorentz indices, but it doesn't take care of gauge indices because this is doublet, this is singlet, so there's an I free. Next I contract that I with the Higgs field and I get a 3-point coupling, Higgs fermion called the Yukawa coupling. The good thing is the Yukawa coupling is perfectly gauge invariant. Okay, so what are the indices I have suppressed from this thing? Somebody? Lorentz, yes. Okay, so I should have put an A dot here and an A dot here, and then I should add the complex conjugate. Okay, and we'll just do that. Anyway, so these are Yukawa. Now you can see immediately why this leads to a mass term, because phi is going to be evaluated to be 0V plus some fluctuations, and that piece will be V times chi-diagonal chi, and hopefully that will be a mass term. Alright, so that's the strategy. Now let's do it. Now there's one more constraint. I've made sure that this is SU2 gauge invariant. I've made sure that this is Lorentz invariant. And I can make sure that it's SU3 gauge invariant in case these are quarks, because the SU3 index won't care about anything else, it will just contract. What does that leave? There's one thing more I have to check. What other invariance does it have to have? U1, very good. And I haven't made sure of that. So if life is good, then when we add up the hypercharge of all these things in this, we better get 0. Okay. That also turns out to be quite important. So let's start with, it doesn't matter quarks or electrons. So let's start with quarks. QL, RU, L, okay, and being left-handed, these are undotted. Left-handed is the same as undotted. So they are like UL, A, DL, A, where A goes from 1 to 2. Now we want a mass term involving these with their right-handed counterparts, UR, which is dotted, or DR, which is also dotted. Okay, let's start with dr. Okay, so if we use dr, then here's dr a dot. Following what I just told you, I need to take q, which is undotted, and I need to dagger it to make it dotted. Okay, so ql dagger has a dotted index downstairs, but then I know how to raise it with an epsilon, so I'll assume I've already raised it, and I'll put the index there. Okay. Notice that this is the coupling of a right-handed to a right-handed fermion, which is exactly what we expect in the two-component spinor notation for a term in the Lagrange. Okay, there will be a complex conjugate at the end, which will take care of the left-handed to left-handed. Physically, it's not a transition from a right-handed to right-handed, because a term in the Lagrangian should be thought of as the in state and the conjugate of the out state. So this actually is propagating a right-handed into a left-handed fermion. These are all things that you should know from field theory. Okay, think of a scalar field when I have phi star phi. Okay, phi star phi doesn't mean that a phi field comes along and turns into a phi star field. Of course, it means that the phi field comes along and turns into another phi field after colliding with its own mass term. Okay, but this is the in field and that's the outgoing field, which is why it starts. So to think of this the same way. But this is not complete because I have suppressed the I index on this doublet, which is the index such that Q1 is U and Q2 is D, the SU2 index. Now, how does that SU2 index behave when I dagger the field? Earlier it was a down index. Okay, it turns out that after I dagger it goes up. So in parenthesis we'll say that SU2 weak, the index is I equals 1 and 2, and any field daggered, for example the Higgs field itself, phi I with I equals 1 and 2 are the two components of the Higgs field, phi plus and phi 0. If I dagger it or star it, then it becomes phi upper I. This is the correct behavior for a real SU2. In this complexified SU2 that we encountered earlier occurring in the Lorentz group, on the contrary, daggering just exchanges an undotted for a dotted index. Okay, but in this, the daggering sends the index up, and of course that's consistent with the fact that phi dagger phi is an invariant of SU2. Okay, because we know that contraction of an upper and lower index is an invariant of SU2 that we already showed. Okay. So that means that this index is I, and now the last thing we need to do is to multiply it with the Higgs field, and we've got our Yukawa coupling. But we better check quickly that this whole thing has vanishing hypercharge, everything else we were short. So what's the hypercharge? For the left-handed guys, it was, so Y is, it was 1/3 for this doublet, but we've daggered it, so Y is now minus 1/3 for this. Okay, for D it is, we just did it. Who has the D right hypercharge? Minus 2/3. And of course the Higgs field we fixed last time to have hypercharge 1, and so we're in business. Okay. Now however, if we repeat the same exercise for the Yukawa coupling between the left-handed quark doublet, oh by the way, before that I should just say that in terms of notation, this thing plus CC. So notation will be Q dagger L phi D, right? So this is how Yukawa couplings will always look in this course. Okay. What you have to remember is SU2 weak index goes between these two guys, and the Lorentz dotted index goes between those two guys. These are the two indices I've drawn out here explicitly. And there may be an SU3 index also. If they are, in this case, there's an SU3 index also. In fact, because these are quarks, but I haven't even bothered to write it. Okay, because the daggered quark and the quark between them, the SU3 index just makes a singlet, and that's it. Okay. Now next, let's try the same game with Q dagger L and QR. So we've only found Q dagger with the right down quark. Now we should do it with the up quark. We have to do this exercise for everyone. Okay. Why do we have to do it for everyone? Because at the end we have to see what mass term comes out. What's going to come out from this product is not a mass term involved. This actually involves both U and D, but the mass term will only come out as D dagger D. That's because the Higgs wave is only in the lower component. Okay, so this term is only going to give me a mass term for D. Okay, so I need another term to give me a mass term for U. Moreover, that other term should give me an independent mass term because the U and the D don't have the same mass, nor does the neutrino and the electron have the same mass. In fact, no two fermions in the standard model have the same mass. So we need an independent mass term for everybody. Okay, so therefore we definitely need such a mass term. The problem is the hypercharge assignments don't work anymore because I get minus 1/3 for this and plus 4/3 for this, and so the total is plus 1. So I can't put in the Higgs phi. So what should I do? I put in phi dagger. Thank you. So I put in phi dagger. Actually, what I do is I put in a field called phi c for charge conjugate. Phi c is the charge conjugate of the Higgs. And the way it's defined is that I take first I take phi, then I star it. So earlier it had a down I index, I star it so it gets an index up, and then I lower that index back with an epsilon. So this is phi conjugate phi, and this will work. Okay, so this actually has the same SU2 properties as the original phi, namely one down index. Okay, but it's obtained by starring as well as multiplying by epsilon ij, which some of the textbooks call I sigma 2, which is another name for the same. Okay, so we learn that the Yukawa coupling between left-handed doublet and the up quark involves a conjugate Higgs, with the down quark it involves a ordinary Higgs. Okay, and that takes care of the quarks. For the leptons, of course, it's very similar. The up quark behaves like the neutrino. It's the upper neutrino behaves like the up quark. It's the upper component of the doublet. So if we were to write a term, which we are not going to write because we are ignoring neutrino masses, it would be like this. And for the electron, it would be like this. So let's summarize all that. And okay, and every hypercharge assignment works fine because in the case of leptons, these individual numbers will be different. But it's easy to see that this and this will again add up to -1 in the case of the electron, right electron, and they'll add up to +1 in the case of the right-handed matrix. You can check all those things. Okay. So to summarize, ignoring neutrinos, we have three mass terms, and they can be called. Now again, this is DGR notation. The mass term itself is Q dagger L phi dr, and Q dagger L phi conjugate dr, and then L dagger L. This is the left-handed electron doublet, and E. So there are these three, ignoring the one responsible for neutrinos, and each of them should have an arbitrary coefficient. That coefficient is usually called F, but actually we are now going to call it F star because apparently that's a good thing for supersymmetry, and we are also going to put a minus sign. It's just convention, just a name for this thing. The important thing is that these F's are all independent, and the minus and the star are just conventions. The important thing is that there are three independent coefficients. Okay. Actually, for the standard model, of course, they are real. Okay. In the supersymmetric case, they may be complex. In the standard model, they are just real. So the star means nothing, and the minus doesn't mean very much because a fermion term m psi bar psi and minus m psi bar psi is exactly the same thing. All physics depends on the square. Okay. So now it's time for us to extract from this, give the Higgs a wave. So the wave is phi equals 0 v with the 1 by root 2, and it's easy to calculate that phi c is v0. Okay. So this is great because this having a v downstairs is we are going to calculate this, and we'll find minus f star d times d L dagger R, okay, times v divided by root 2, then minus v f star of u divided by root 2 times u L dagger u R, and finally minus v by root 2 f star of e L dagger e R. And with this, except for the neutrino, we have managed to get a mass for all the fermions in the first generation. moreover, 3 arbitrary parameters. So 3 arbitrary masses. In fact, every fermion in this model has an arbitrary mass. It can only be fixed by experiment. Is this much clear? Any questions? The masses are identified as m. Let's say m of the down quark is just minus v by root 2 f of the down, etc. Now, one beautiful consequence of this mechanism, well known of course in phenomenology, but I think it should be amusing to those of us who are thinking about this afresh, is that if a quark is heavy, then like the top and bottom quarks, then the corresponding f has to be cranked up to be a large number. Okay, but if I do that, then I'm also cranking up the Yukawa coupling of that quark with the Higgs. Okay, because the physical Higgs also is contained in this. This is the Yukawa coupling, and phi has to be replaced by v plus eta. So besides giving a mass term, with the same strength it gives a phi d bar d coupling, which means the Higgs interacts most strongly with the heavier quarks. Okay, so these are kind of things that are peculiar to this model, because we have got masses generated out of Yukawa couplings via the Higgs mechanism. We have to live with the fact that phenomenologically the Higgs will interact more strongly with the heavier quarks. So these are little, these are facts which are of course verified in experiment or will be verified, but they're so easy to see just because of the basic gauge structure of the model.
If the weak interaction was not this left,
yeah,
then if we had a doublet there also,
yes,
then we won't need.
That's correct. Thank you. And that's a very good question. Supposing we had a left-handed doublet and a right-handed doublet, we would get the following very simple things, all of which would be in conflict with experiment. First of all, there would be mass terms possible. Okay, so you would have direct mass terms, not through a Higgs mechanism. Okay. However, in that case, the upper and lower component of the doublet would have the same mass term. Okay, supposing I take the doublet, the quark doublet or the lepton doublet, neutrino and electron, dagger it and multiply it with its right-handed counterpart and put an m, then the neutrino and electron must have the same mass. That's the end of that model. Even if that wasn't the end, we would find it hard to incorporate or impossible to incorporate parity violation. Okay, parity violation is precisely the statement that left and right-handed electrons or quarks couple differently to the weak interactions. Okay, and there's one more thing which would go wrong, which I can't remember. But in short, we would be forced to obey constraints that are too tight, and the model doesn't survive right in the beginning. So in that sense, the standard model has a good degree of freedom without having way too much. We'll summarize a little bit how much freedom there is in a few minutes. Okay. Now, one of the key properties of consistency that the standard model passes is called anomaly cancellation. If this is something you are not very familiar with, I would strongly recommend you go and look at the relevant chapters of Peskin and Schroeder's book, which is particularly good on this. And in fact, Cheng and Lee have a treatment of anomaly cancellation in the standard model that I find, let's just say, suspicious. I think it's not even actually precisely correct, but it seemed quite misleading to me. But these guys are more careful. And the basic constraint for anomaly cancellation is that the trace properly defined over the spectrum of particles of the generators Ta, Tb times Tc have to be 0. Okay, this conceals more than it reveals, of course, because in general the trace comes out 0 because the trace can come out non-zero only if there is a chiral spectrum of particles. So the contributions in this trace will have some things with plus from left-handed and some things with minus from right-handed. If the particle spectrum is completely, or the interactions are completely symmetric between left and right-handed, if there is no parity violation, then this is already 0. Okay, so the thing to check involves the chiral spectrum of the particles, and these T's are generators of either SU3 or SU2 or U1. Okay, so you can put in all possible combinations, but most of them turn out to be zero quite naturally. For example, if these are all generators of SU2, then this is already zero, because TATB anti-commutator is delta AB, okay, at least in the fundamental of SU2. Take that out and trace of TC is zero. That kind of relation is already obvious. So you need to look for the troublesome traces to calculate. And as you probably know, the fact that this is cubic in generator comes because the diagram corresponding to the anomaly is a triangle diagram with three external gauge bosons. And we have the choice of these gauge bosons being any of them in U1 or SU2 or SU3. Okay? Good. Now, and we are talking of gauge anomalies, not anomalies in global symmetries. Of course, anomalies in global symmetries can be there, they will have some physical consequences. But if the anomaly is in a gauge symmetry, then the theory is inconsistent right there. Okay. So it turns out that now, again, you can evaluate these either using the physical theory or the theory before Higgs mechanism. It's always easier to do before because that's where all the gauge groups are much more clear and there's no mixing. So this U1 is therefore hypercharged, and this is the left and left. This is the SU2 that couples only to left-handed particles as doublets. So this is one possible source of anomaly, and in this case, the trace in question is the sum of over only left-handed fermions of the hypercharge of the left-handed fermions. So the anomaly cancellation tells us that if I add up the hypercharge of all the left-handed fermions in the standard model, I will get zero. Okay, that's a bit alarming because we didn't bother up to now to add up these things and check whether it gives zero. So if it fails this, then whatever I said last time and this time is all completely useless. There's no quantum field theory corresponding to this classical theory whose Lagrangian have been writing about. Okay, so let's do this. For this, we'll need everybody's hypercharge assignments, and we'll also need to check the degeneracies carefully. This is a sum over all fermions. So, for example, if this lies in a doublet, then there has to be a 2. If it lies in a triplet, there has to be a 3. So, this is twice times minus 1, which is the hypercharge of the left-handed lepton doublet. Okay, LL plus for the left-handed quarks, they are in a doublet. Well, but the doublet, yeah, they are in a doublet. They are also in a triplet, so there's 2 times 3, and the hypercharge was chosen to be plus 1 by 3. This is the quark left-handed doublet, and we see that this is 0. Okay, is that clear? This 2 is for the neutrino and electron. This 2 is for the up and down quark. This 3 is for the triplet color indices of the quarks which are suppressed. And we see that the whole thing adds up to 0, but it wouldn't add up to 0 if there were, let's say, only quarks or only leptons in the world. So it's rather an amazing, this is the first thing I think in all that we have discussed up to now since last time, where the quarks and leptons have to play some cooperative role. Otherwise they were completely free to exist or not. Any number of them could exist. We would have been able to find some doublet structure and all if they fell into doublets with some suitable hypercharge difference of 1, we would have been able to accommodate the spectrum. But this would rule out lots of models, and it doesn't rule out this one. And of course it's consistent with the fact that you have 1/3 charge for the quarks, but then you have 3 quarks. Okay. Now amazingly, if there were not 3 but n quarks, let's say we were working in SUN gauge theory, for some reason we just extended QCD to an SUN gauge theory with n being arbitrary, then of course the quarks would have charge 1 by n and there would be n of them, so this condition would go through. But this isn't the only condition, there's another condition, and so it's clear that it's a fairly constrained system, although it also leaves open fairly many possibilities, by no means unique. Okay. So the other dangerous diagram turns out to be when you have 3 U1 gauge bosons, and then it is a statement that the sum over the hypercharges of the left guys cubed minus the sum over the hypercharges of the right guys cubed. is 0. Okay, so let's evaluate this one. The left-handed leptons give me 2 times minus 1 cubed, and the left-handed quarks give me 2 times 3 times 1 by 3 cubed. Okay, so this is minus 2 plus something here. This doesn't look very convincing. Yeah, but it's true. So this is plus 2 by 9. Okay, that's minus 16 by 9. That's this one. This term is over the right-handed fields. So for the right-handed fields, we have 3 quarks, up quarks with hypercharge 4/3. We have 3 down quarks with hypercharge minus 2/3. And we have 1 right-handed electron with hypercharge minus 2. And the neutrino has hypercharge, right-handed neutrino has hypercharge 0, so it doesn't contribute to this equation. So we add up these 3 numbers and we get 1 by 9 into 64 from here, minus 8 from here, and then minus 8 and so this comes out to be minus 1, 7 plus 1 by 9, 6 plus 2 by 9 minus 8, so it's minus 2 plus 2 by 9, which is the same as it. So that's the benefit. Okay, so this is a very important consideration for the standard model to be consistent at all. There are some other anomalies, but most of those potential anomalies, but most of those vanish more trivially. Okay, Peskin and Schroeder has all some 8 diagrams of different kinds of anomalies, and most of them are guaranteed by much simpler considerations. But these are the 2 that are absolutely not guaranteed unless you have really chosen the field content and representations in detail, and the fact that it works out equations. And of course, anomaly cancellation is generation by generation. So if we add, it means, this is very important in fact, again a phenomenological consequence. Let's say we only knew up-down, charmed and strange quarks, which was the case up to around the mid-70s. I think the charmed quark was discovered around 76 or something. And we knew, of course, neutrino, electron-neutrino, the electron, the muon and the muon-neutrino. So we have 2 generations of quarks and leptons. If even a single new quark or lepton was found, that is, if we either found the top or the bottom or the tau or the neutrino of the tau, we would be forced to postulate all the others. Okay, because everything has to come complete in a generation. So if even so now there are 3 generations and we don't think there are any more because of cosmological and other considerations. But if there were one particle that has to be in the 4th generation, and if it was let's say a lepton, then for consistency the model has to contain a full quad, doublet and triplet of that generation. That's quite impressive. Okay. Good. So I have mentioned generations, so now it's time to talk about them. So corresponding, it's very easy of course to extend the standard model at this level by putting in left-handed doublets. Okay, as it happens indeed experimentally we know that all of these have plus 2/3 minus 1/3 electric charge. Okay, and then for the leptons we have mu e, mu tau, all left-handed. Okay. Then we have right-handed singlets, and they are just all of them. So boring to write down. Okay, and the charge assigned, the hypercharge assignments will be copied from generation to generation. generation, and that's the full fermion content of the standard model. 3 of these are new in a sense. The right-handed electron, muon and tau neutrino were added only after it became clear that neutrinos have a mass, only in the last few years. So most of the textbooks, Cheng and Lee, and actually even Reis-Tortole and Roy sort of are working with standard model in which there are no right-handed neutrinos at all. But a later chapter in DGR deals with the neutrino mass problem. Okay. Now with this, we obviously need some notation if we are not to keep writing all these things. So this whole set we'll summarize as QIL, where small I is a generation index 1, 2, 3. Okay, and these will be Li left with the same index. And these similarly will have I, but the notation is a little in a way it could be obscure, so you better get used to it. If I say up right with the generation index, then it means the up type quark in the first, second and third generation, each of which is a right-handed singlet. So it means the up, the charm and the top quark. Those are UIR. U, C, D. And the down type are D, S and B. Okay. And similarly, electrons and neutrinos. Other way around. UIR. Okay, so this notation takes care of all the fermions, and it carries an extra global index small I, which goes from 1 to 3, which is the generations. Good. Now that we have the generations, we notice that nothing in all the consistency or symmetries of this theory prevents us from writing extremely general mass terms. We are not obliged to write mass terms which only connect the U left to the U right. In fact, the U left can be connected to C right and T right as well, and it's perfectly natural. So, in a generalization of the terms I've already written, the Yukawa couplings I've already written, I'll write minus F star down type with a lower indices I and J times the left quark doublet with this I and the right quark doublet with the J, and nobody says that Fij has to be diagonal in small I and small j. If it was, that would mean that the masses are there only within generations, but that exactly is not the case, and the first experimental indication for that came long ago, and it involved what? Flavor changing, thank you. And the angle associated to that is the Kapiva angle, thank you. Exactly, so the mixing between the down and the strange quark. Okay, so this has been known for a long time, and now with 3 generations, then of course in general there can be mixing between all the quarks, but as we will see, it reduces to a set of a smaller number of parameters if we make use of all the symmetries of the problem. So here's Q dagger, I left, phi charge conjugate, and the up type quarks, and finally F star Ij of the electron, left-handed electron doublets, phi and right-handed electron type singlets. Okay. So these are 3 independent 3x3 matrices. Okay. These are the Yukawa couplings. What happens when I put in the web of the Higgs is quite obvious from this. So this leads to minus Fij d over root 2 d dagger I left phi d j right, etc. Okay, this comes from the first term. Phi is replaced by v in it. Sorry, there's no phi anymore. Phi is replaced by v over root 2, and it's the down component, so we get d dagger d. So here's the mass term, non-diagonal mass term. Okay, so it's natural to call this thing Mij of type, this is type D. So it's the D quark mass matrix. Okay, so the D quark mass matrix, if you like, tells me mixing among this, this and this. Okay, it's pretty clear from the symmetry structure that I can't have mixing between this and that. Okay, the mixing has to be between bottom components or between top components, otherwise it wouldn't respect the SU2 doublet structure. So at the end of this, I've got 3 mass matrices. So the mass terms at the end of this across generations are Mij of D, D dagger I left, D J right, plus Mi, just blindly repeat this thing, U type, U I left, J right. And that's it. Now it's quite natural to try and get rid of whatever we can get rid of by making suitable transformations on the fermions. And what you can see clearly here is that you can diagonalize each of the mass matrices if you make an independent unitary transformation on D right and D dagger left. Okay, these matrices are not Hermitian, they are not even symmetric, so they cannot be diagonalized by a single unitary transformation. But they can be diagonalized by taking a unitary matrix on this and another one on this. So let's write it. So let's assume that DJR goes to U, J, K, D, K, R. I think in my notation it's inverse. This is called U inverse. And I should label the U, so it's a U of down quark type. And let's assume that this should actually U of down right quark, right? DJL is going to go to U, JK, PK, L of left down quark type. This -1 is inverse. So let's just do this. There could be in principle subtle effects associated with non-invariance of the measure of the theory under this, okay, which is associated in turn with CP violation, but we are not going to discuss that just now. So when we do this, you can see that the mass term goes to Mij of the down quark goes to U down left dagger Mij. So M down U down right I. This is what I meant when I said that you get one unitary transformation on the right and another independent one on the left. Okay. This is called a bi-unitary transformation. The phenomenologists get very excited when they say the word bi-unitary. It sounds very deep, but it's only this simple thing. And with this, you can actually diagonalize just about any matrix you like. Okay, so you can diagonalize it by doing this thing. Now, of course, you see what's going to happen. We've defined a different, this one should not worry you, but this matrix should worry you, because we've given a label to U of the down quark left-handed, okay, and this implies that when we do the same exercise for the left-handed up quark, we'll be free to choose another U, okay, but if we are going to choose a different U for left-handed down quark and left-handed up quark, then we are destroying what? The I3, the SU2 doublet structure. Okay, so that's the one that contains, if you like, the non-trivial information, because finally, if that is the case, that we really have, the point I'm making is that these are phenomenological parameters, and so we may have to do it. We may really have to diagonalize, the matrix which diagonalizes the up quark mass may not be the one which diagonalizes the down quark mass. Okay, and therefore the difference, if you like, which is measured by taking dagger of one times the other, is a matrix which is there in the model, which is messing up the doublet structure, and which is that part of the mixing which doesn't really commute with the doublet structure, and that's the one which is physically important, and it's called the Kabibo-Kobayashi-Maskawa matrix or CKM matrix. So let's write its definition. Define Vij 3x3 matrix associated to the left-handed quarks. There will be another 1 associated to the left-handed electron neutrino, electron and neutrino, leptons. But this is the quark one, and it's the matrix U which diagonalizes the up quark, and it's the left. It's defined here. Same thing, the D replaced by U. This dagger and then U, D left, not dagger. This whole thing I take. Okay. And now you can see that if the same matrix could be used on the left up and down quarks, so that this biunitary transformation diagonalizes the mass matrix, then this U dagger U would be 1 and the matrix we have defined would be 1. Okay. So Vij is the true measure of mixing, if you like. Why is it the true measure of mixing? Because to the extent that this is 1, then we would make these transformations already and we would manage to have our doublet structure and generation structure such that the mass terms are diagonal within each generation. Okay. The only reason we can't assure that is when the lower components of the doublets mix while the upper components of the doublet don't mix in the same amount. Okay. This also shows us that we can undo the mixing of the upper components as a convention. So in fact, if I have U, D, C, S, D, B as 3 doublets, I can always pretend that U, C and T don't mix. That's because I perform these transformations until U, C and T don't mix. Okay, but then because of this non-trivial matrix, D, S and B mix, and this is the matrix which measures the mixing. Okay, and you remember that the Cabibbo angle is the mixing between D and S. Okay, but now that we have a 3 by 3 matrix, we'll have to diagonalize it carefully and see what the physical meaning is of all the parameters.
So this SU2 thing still remains assumed? SU2 the SU2
No, the mass eigenstates are not SU2 eigenstates. Okay. That's a fact which is guaranteed if this matrix is not 1. So the SU2 doesn't commute with mass. That is just a fact of the model. Okay, again, it's a experimental fact. Experiments could have told us that the mass matrix doesn't like to mix across generations.
How can you fix that? It's 1 for the...
By these.
No, but physically, if there is a mixing, there is a mixing.
How do you define U and C? What's the difference between U and C? They have the same electric charge, they have the same I3, they have the same color triplet nature. What's the distinction? Okay, mass. But then the whole point is that the distinction on grounds of mass makes sense only after I made the mass matrices for these diagonal. Then they have a mass, otherwise they don't have a mass. Okay, so what I can do is say that U, C and T are mass eigenstates always. Okay, now I can't say that D, S and B are mass eigenstates. I have to say the D, which is the bottom partner of the U, is not a mass eigenstate, but the mass eigenstate, which is a linear combination of D, S and B, is not the lower partner of a U, but it's the lower partner of 3 different guys mixed up. Okay, so that's why this is the true measure of mixing. You explained that, and it's called the Cabibbo. Interested to know that Cabibbo is the Italian variation of the Semitic name Habib. Okay, he's actually Italian, Jewish Italian. Okay. Very good. So to conclude this lecture, is this all clear? We're not going to go into this matrix in much more detail now. However, for those of you totally unfamiliar with this sort of thing, of course, you should look at the 2 by 2 version. Okay, the 2 by 2 version is just the Cabibbo matrix, if you like. Kobayashi and Masukawa taught us how to understand the 3 by 3 version of this. And the 2 by 2 version eventually boils down to 1 mixing angle. That's the Cabibbo angle. Okay, the 3 by 3 version contains more subtleties. But since this is not an in-depth review of the standard model and I want to start MSSM next time, I'm going to just go this far. And then whenever we encounter the subtleties in the supersymmetric case, we might have to refer back to the usual standard model. Okay. So the last thing I want to do now, and it's the easiest by far, is to tell you, roughly speaking, what are the experimental values for the standard model parameters. Partly to give an orientation, and partly also to show you how many experimental answers we need to fix the parameters. After all, we have written down lots of parameters by now, and we haven't kept careful track which are independent and which are dependent. So the question is, how many measurements do I have to make to fix these things? And I'm not fanatic about the accuracy of what I'm telling you, but I did check this year's particle data tables, so I think within 1 or 2 decimal places I'm probably okay. So here are the things that can be measured in experiment: mass of the W, mass of the Z, mass of the Higgs, mass, and the electron charge, the electric charge, quantum of electric charge. So electronic charge. So what are the values for these? First of all, let's write out what the standard model predicts these to be in terms of other parameters. This is the coupling constant of the SU2, G2, times the Higgs wave over root 2. Okay. Mz is the same thing with G2 replaced by the square root of G2 squared plus Gy squared. But that's the same as G2V over root 2 times cos theta W. Okay. The Higgs mass we did today, it's root 2 mu. And the electric charge of the standard model is G2 times Gy over root G2 squared Gy squared plus G2 squared, and that's the same as G2 sine or cos. I'm not sure, I think I have it written somewhere. What is it? G2 sine theta W?
Gy cos theta.
Huh?
G2
sine theta W or Gy cos theta W, which is the same thing. I'm just trying to keep the parameters in terms of G2. Okay. So this is the set of things that we can measure, and we know the answer. So let's also write the answer. So the W boson mass is, anyone? Thank you. Really very close to 80. In fact, it's just 80.4. And the Z mass is 91.2 GeV. I already said this last time, but the fact that this is greater than this is the fact that cos theta is less than 1. So this formula being a prediction of this model, if we found a Z to be lighter than the W, that is the end of the standard model. So you can see how many tests it's actually passed, which are extremely robust. You just cannot fiddle this thing. I mean, this has to be greater than that. Last time I said it by pointing out that the coefficient here is square root of Gy squared plus G2 squared, and that's clearly greater than G2 itself. So this has to be greater than this. Okay. Higgs mass we don't know. As of what I could find out today, the standard model Higgs mass is officially bounded below by 114 GeV experimentally. Okay. There's also an upper bound beyond which the standard model isn't predictive anymore. That has to do with the because if it's very large, then mu is very large. Okay. But mu being very large, for fixed V makes lambda very large. And if lambda becomes very large, then the Higgs sector becomes strongly coupled, and then we don't really know whether anything we are saying about this model makes sense. Okay, so that places a kind of theoretical upper bound, which is about somewhere around 300 or 400 GeV, I think. And so that's the window in which the Higgs better be found. But of course, that's the standard model Higgs, and soon we'll be discussing the MSSM Higgs, which is quite different. For one thing, there's not one particle anymore, there will be many. Anyway. So what we can see from this is that because sin theta W and cos theta W are in turn defined, cos theta W is G2 over square root Gy square plus G2 square. So you can see that G2, Gy and V can be determined from these measurements. For the last one I didn't write, what's the electric charge? That of course depends on a choice of units. We'll work in units where H bar and C are 1. Not the units of coulombs, which is an actual unit for electric charge. So when H bar and C are 1, then E is 0.303. Okay, that's because E squared over 4 pi is 1 by 137. That's the fine structure constant alpha. Okay, so from this number, and this number, we can certainly read off G2, Gy and V. Okay, because this is fixed in terms of G2 and Gy. This formula is given in terms of G2 and Gy, and the only other thing you need is V. So 3 things you can read off right away. So these we know. There's no mystery about them. And the answer is G2 is 0.646, Gy is 0.732. By the way, these I should say I didn't get from anywhere, I calculated it myself, so there is a very good possibility of an error. Okay, so if you have any doubts about these numbers, please check them yourself and tell me if I got it wrong. This one I got at the end of my calculation, and I got this number, while Cheng and Lee said it's around 250 GeV, so I got some confirmation. And if you plug these two things into this formula, then you get that sine square theta w. So normally when Weinberg angle is quoted, you are always told the value of its sine squared. You should be careful about that. So if you want the sine, you have to take the square root of this. So it's about 0.22. Okay, but this is not a fourth parameter, of course. This is just a combination of the first two. Okay, so those are all fixed. What does that leave unfixed? The Higgs mass, which is the same as not knowing mu. But if we knew the Higgs mass, then we know mu. Since we also know V, therefore we would know lambda. So that would complete all the coupling constants other than the ones involving fermions. For the fermions, we know that the parameters, so the remaining parameters, are the ones which give you the fermion masses and mixing. Okay, mixing part is in CKM and the masses are just there. Okay. So between all these are all the standard model parameters, and I'm not so concerned now, right now, to work out what we know about fermion masses and mixing from experiments. Somehow this is conceptually clear. There's nothing except experiment which fixes the fermion masses and mixing. So whatever it is, we would measure it sort of directly. The masses of the fermions we would measure sort of directly. Of course, quarks are confined, so there's an issue of how to define the quark mass and all that. Electron masses, of course, we know very well. And mixing, in order to do that, we would have to go into what are all the different angles that come out from the CKM matrix and what they mean and so on, which is quite a long story in itself. But I think this summarizes what we need to know right now about physical parameters of the standard model. And it's also where I'm going to stop. Now next time I think we are on track to start the MSSM next time. The only little thing I didn't get to work out in time to tell you was the discrete symmetries of the standard model, which I think might be important. So there might be 5 or 10 minutes next time for that, and then we'll start on the MSSM. Any questions?
Nice that G2 came out less than 1.
Yeah, that's extremely important. Thank you. And Gy, I think both came out less than 1 is very nice. Yeah. Another thing, of course, this is an old comment that, in fact, I think Witten was the first to highlight this, that E being 0.3 in units where H bar and C are 1 puts it at the same value as 1 by n when you do 1 by n expansion of QCD, because n is 3 in QCD. Okay, so when you say n is 3 and I'm going to expand in powers of 1 by 3, people initially laugh and say 1 by 3 is not a good parameter, but then E is also 3, and in fact this is a fantastic expansion parameter, the best in the history of physics, so we shouldn't be too discouraged about the 1 by n expansion. But as we see, even 7 and 0.7 and 0.6 are good, probably even greater than 1 would not have necessarily been bad, because as we know, we have to square it and divide by 12 or pi, so to get something that's really physically relevant. And so I think we could have quite easily lived with the value even 2 perhaps, or 1.5. But probably it would get worse and worse beyond 1. So we are lucky that it comes from this way. Okay.